Раз, два, три, раз, 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 два, три, раз, раз, раз.
Хорошо, спасибо за экономию.
Нет, я тоже представлю. Ну, я список как бы Attention, please. It's a privilege for me to chair this session, and I hope that Denise and me will ensure that the session will run smoothly, and but at the same time, the cooperation from the speakers would be very much appreciated. And now I'm going to introduce our first speaker, Professor Valery Labonets, who is a full member of the Academy of Engineering Sciences of Russian Federation, and he is an expert in developing of digital algorithm for the analysis of signals and image recognition. He is the author of more than 200 papers, including 4 monographs. So the floor is yours.
Thank you. Dear colleagues, my English is not very well. For this reason, I'm going to speak Russia. Is it okay? Моя презентация носит интегральный характер и объединяет 4 доклада, которые приняты на нашу конференцию. Значит, первый доклад «Ваш покорный слуга» и Екатерина Остхаймер, это USA, Prometheus Incorporation. Следующий доклад, часть 2, примеры многопараметрических преобразований, 2 предыдущих автора, и еще 2 появились новых, Часовских и Сметанин. Один из Уральского федерального университета, другой из Бауманского университета. Третий доклад противоподслушивающие и антиглушительные свойства системы ОВДМ, основанной на многопараметрических вевлет-преобразований. Ну и 4-й доклад, то же самое, связанное с многопараметрическим преобразованием Фурье и дробным преобразованием Фурье. Содержание презентации представлено на этом слайде. На первый пункт я расскажу, что представляет собой классическая ОФДМ технология. Затем остановлюсь на многопараметрических преобразованиях. Это самый главный математический аппарат, который будет использован для проектирования нового поколения ОФДМ-систем. И здесь целый перечень многопараметрических преобразований, которые в цифровой обработке сигналов, к сожалению, большого применения не нашли. Ну вот здесь я очень люблю эти преобразования, и вот в этой тематике я нашел им, как мне кажется, хорошее применение. Ну и дальше свойства этой системы. Самый главный упор делается на то, какими противоподслушивающими и свойствами против перехвата конфиденциальной информации такие ОФДМ-системы обладают. Ну и какими противопомеховыми свойствами эти системы обладают и в сравнении с классической ОФДМ-системой. Вот примерный план моей презентации. Итак, первый пункт. Что есть ОФДМ-технология? Значит, вот здесь представлена блок-схема классической ОФДМ-системы. Имеется источник информации, который генерирует битовый поток. Там имеются АЦП, которые оцифровывают все аналоговые сигналы, какие нужно отправить. Формируется бинарный поток, который отправляется на обработку. Этот бинарный поток поступает в память компьютера, выхватывает там комплексные числа. Я чуть-чуть попозже расскажу. Эти комплексные числа модулируют гармоники. Классические гармонические сигналы, которые называются поднесущими. Этих поднесущих n штук. Затем эти все гармоники суммируются, подаются на цифроаналоговый преобразователь, получается аналоговый сигнал. Этот аналоговый сигнал поступает на амплитудный модулятор, обычный классический амплитудный модулятор, насаживается на несущую частоту, она излучается, поступает в канал связи. В канале связи имеют место тепловые помехи, которые добавляются к этому сигналу. Сигнал поступает на приемник, усиливается, демодулируется, снимается вот этот вот групповой сигнал, подается на аналогоцифровой преобразователь, осуществляется быстрое преобразование Фурье, извлекаются эти комплексные числа, из этих комплексных чисел формируется бинарный код. Чуть-чуть подробнее это расскажу, потому что на блок-схеме не совсем ясно идет изложение. Итак, битовый поток. От нуля, от старта до бесконечности бегут нули и единицы. Эти нули и единицы, этот битовый поток разбивается на сегменты. Этот сегмент называется ОФДМ-символом. Длина сегмента равняется m умножить на n. n – это длина быстрого преобразования Фурье или количество поднесущих, которые вы используете. m – это разрядность адресов в памяти компьютера, где находятся комплексные числа. Самое главное – это совокупность комплексных чисел, расположенных на комплексной плоскости, формирует регулярную фигуру, вот, например, такого типа. Эти комплексные числа нумеруются двоичными числами. Если их 16 штук, то нужно 4 разряда. Вот это m – это раз 4 разряда. Если здесь будет 256 точек, это называется сигнальное созвездие. Если 256 точек, то 8 разрядов для нумерации всех комплексных чисел. Значит, здесь будет m, и вот эти вот прямоугольнички будут длиной 8. Таким образом, если вы используете 1024 поднесущих и 256 звездочек, то 8 на 1024 – 8К. 8К длина вот этой вот последовательности. Итак, каждая четверка поступает, формирует адрес. По этому адресу в памяти находится конкретное комплексное число. Оно извлекается и становится первым комплексным числом в векторе, второй, третий, четвертый, пятый. Затем на этот столбец длиной n или размерностью n действует обратным преобразованием Фурье. Получается дискретный групповой сигнал. Этот дискретный групповой сигнал поступает на цифроаналоговый преобразователь. Получается аналоговый сигнал вот подобной, так сказать, формы. Этот аналоговый сигнал, как я уже говорил, поступает на амплитудный модулятор, излучается и вперед на приемник. Поднесущие, виды поднесущих. Ну вот матрица Фурье. Здесь столбцы гармонические сигналы, константа, первая гармоника, вторая гармоника, третья, четвертая, пятая. Ну и если я на столбцы Z действую преобразованием Фурье, то видно, что групповой сигнал – это сумма взвешенных гармонических сигналов с весами Z0. Ну еще вернусь назад, скажу, каждое комплексное число, оно как бы несет с собой адрес. То есть комплексные числа, которые вот здесь расположены, они вот этот как бы содержат в себе вот этот адрес. И по этому комплексному числу на приемной стороне восстанавливают адрес и битовый поток. В нашей работе вместо преобразования Фурье f-1 будет использоваться многопараметрическое преобразование, о котором речь чуть-чуть впереди. Это простая модификация, которая затрагивает только программное обеспечение классической OFDM-системы. Спецпроцессор быстрого преобразования Фурье заменяется на спецпроцессор быстрого многопараметрического преобразования, либо программа чуть-чуть модифицируется. Итак, модификации какие? Ну, вы сразу понимаете, что ученые бросились модифицировать эту систему. Все, кто занимался обработкой сигналов, попытались использовать в своих работах преобразование Уолша, преобразование Хара, Вевлет преобразование и так далее. В результате накинулись и модифицировали, ну, в надежде, что получатся системы с лучшими тактико-техническими характеристиками. Да, некоторые характеристики улучшаются, некоторые ухудшаются и так далее. В настоящее время это широкий фронт работ, и все ортогональные преобразования пытаются применить здесь и пытаются посмотреть, какое ортогональное преобразование лучше всего подходит для решения задачи эффективной передачи информации. Чисто визуально, как выглядят гармоники. Дискретное преобразование Фурье, гармоники. Константа, первая гармоника, вторая, третья, четвертая. Это на выходе интерполятора, например, нулевого порядка. Это прямоугольные. Если используете поднесущие функции Олша, а они вот здесь представлены функции Олша, нулевая, первая, вторая, то поднесущие будут иметь такой вид. Если будете использовать m-последовательности, то матрица будет выглядеть вот таким образом, и псевдослучайные последовательности или m-последовательности представлены справа. Если вы будете использовать преобразование Хара, то поднесущими, которые будут тащить с собой информацию, будут функции Хара, которые вот здесь представлены. Значит, и если вы будете использовать преобразование Хартли, то там базисные гармонические сигналы, это косинусы, сдвинутые на четверть фазы. Вот их вид, дискретный вид, а вот сглаженный цифроаналоговым преобразователем. Вот таким образом выглядят поднесущие во всех классических случаях и те, которые в настоящее время используются. Мы предлагаем использовать многопараметрические преобразования. Что представляет собой такое преобразование? Оно зависит от некоторого набора параметров. Θ1, Θ2, Q. Значит, это матрица, строки есть, но все строки, то есть поднесущие, зависят от набора параметров. Вы изменяете значение параметров, преобразование меняется. Дальше меняете, преобразование меняется. И таким образом вы, меняя параметры во всех его возможных диапазонах, вы можете получить большой ансамбль различных преобразований. И оказывается, частными случаями или реализациями многопараметрического являются все вышеперечисленные преобразования в том числе. То есть не надо тыкаться и пытаться одно использовать преобразование, второе, третье, многопараметрическое позволяет вам широкий класс ортогональных преобразований получить, меняя только одни единственные значения. Вот здесь картинка, которая иллюстрирует только что сказанное. Пространством параметров обычно является многомерный тор. Многомерный тор размерностью Q. Но в данном случае Q равняется двухпараметрическое преобразование. Θ1, Θ2, два параметра, которые параметры бегают по тору. При некоторых значениях это может быть дискретное преобразование Фурье, Уолша, Хара, косинус, ну и так далее. Ну и параметрическим пространством, как я уже сказал, является Q-мерный тор. Q-мерный тор. Значит, если я использую вместо преобразования Фурье, использую многопараметрическое преобразование с некоторыми конкретными значениями параметров, то этот набор параметров является ключом для входа в эту ОФДМ-систему. Если у вас нет этого ключа, то у противника вашего, который пытается вас подслушать или заглушить работу вашей системы, он должен этот ключ найти. А сток сена, в котором вы должны найти этот ключ, является вот это многопараметрическое преобразование Q. Q может достигать значений порядка 15 тысяч. 15 тысяч, то есть это 15-тысячное мерное торообразное преобразование. Найти в этом стоге сена ключ для современных систем радиотехнической разведки – это чрезвычайно трудная задача. Чрезвычайно трудная задача. Более того, вы можете что? В процессе работы телекоммуникационной системы значение этих параметров периодически менять так, как у нас в мобильниках происходит. Рабочая частота каждый через определенный так меняется и все время ищет тот диапазон, в котором лучше всего проходит, так сказать, сигнал. И оператор, и системы оценивают прохождение ваших сигналов. И здесь точно так же вы можете менять эти параметры или эти ключики вы должны менять по периодическому закону, который известен приемнику и получателю заранее. Тот, кто служил в ПВО, прекрасно знает, утром после развода приходишь на станцию, тебе начальник штаба вручает что? Прежде всего рабочую книгу, частот, на которых сегодня радиостанция должна работать и на какой частоте, в какое время вы должны выходить. Здесь то же самое. И тогда противнику перехватить вашу конфиденциальную информацию становится чрезвычайно трудно. Но более того, передаваемые сигналы становятся зависимыми от чего? От этих параметров. Значит, можно эти параметры еще что сделать? Ими поиграть с тем, чтобы оптимизировать те тактико-технические характеристики, которые характеризуют вашу ОФДМ-систему. Например, самое главное – это отношение среднеквадратичной мощности, максимальной мощности к среднеквадратичной мощности. Потому что многие ОФДМ-системы находятся на беспилотных летательных аппаратах, стая летит, стая беспилотников, там порядка 1000 штук, они обмениваются друг с другом информацией, картинками и так далее. И самое важное – энергоресурс. А если пиковая мощность резко возрастает, то источники питания быстро подседают. Поэтому отношение пиковой мощности к средней должно стремиться к чему? К единице. Значит, нужно покрутить, найти такое ортогональное преобразование, в которых это отношение важнейшее было бы близко к единице, например. Или, например, диапазон, в которых работает ваша ОФДМ-система. Он должен быть поуже, потому что радиочастотный комитет следит за вами, как вы работаете, соблюдаете ли вы законы или нет. Вот Ну и теперь история многопараметрических преобразований. Впервые многопараметрические преобразования были предложены, конечно же, великим математиком Эйлером. Ой, Якоби. Эйлер тоже приложил руку. В 1846 году что он сделал? Он ввел матрицу, которая в настоящее время называется матрицей Якоби. На главной диагонали стоят единицы, за исключением P и Q столбца и строки, где стоят косинус, синус и косинус. Это матрица вращения в плоскости, натянутой на p-й орд и на q-й орд. В этой плоскости в многомерном n-мерном пространстве осуществляется вращение. Далее он предложил следующее. Берем любую ортогональную матрицу, умножаем ее, например, справа на вот эту матрицу вращения и ищем такое значение угла у этой матрицы вращения, при котором один внедиагональный элемент обнуляется. Итерационно, используя эту процедуру, можно получить следующее. Вот у нас матрица произвольная. Q. Плюсиком я обозначил вот этот элемент, который хочу обнулить. Осуществляя вращение в плоскости 1, 2. И выбираю угол таким образом, чтобы здесь появился 0. Затем в плоскости 1, 3. Выбираю угол таким образом, чтобы здесь появился 0. Ну и так далее. В результате после n-1 итерации вот здесь получается нули. Эта матрица исходная ортогональная, все матрицы вращения ортогональные, произведение этих матриц ортогональное, значит, эта матрица ортогональная. Она может быть ортогональной только тогда и только тогда, когда вот этот столбец после всех вращений тоже состоит из нулей. Получаем матрицу вот такого типа. Итак, вверху строка нули, применяем точно такую же. А здесь матрица размерностью на единицу меньше. Применяем эту стратегию к этой матрице, обнуляем это, и до самого конца, пока исходная матрица не будет диагонализирована. Значит, в результате любую матрицу, ортогональную матрицу можно представить в виде произведения матриц Якоби. Вот они, тут углы. Но если матрица исходная была фиксированная, здесь фиксированные углы. Ну а теперь вы эти углы можете менять как хотите. И оказывается, меняя углы в пределах от 0 до π, вы пробежите все ортогональные преобразования размером n на n. Любые. Вот алгоритм преобразования. Значит, здесь знаменитая операция типа Butterfly, которая присутствует вообще во всех быстрых алгоритмах. В БПФ, в быстром преобразовании Олша, Хара и так далее. Только здесь вот эти перекрестные ребра, они нагружены косинусом и синусом. В Олше это плюс-минус единички. Это операция, вот она. Таким образом, любое ортогональное преобразование многопараметрическое может быть представлено таким образом. Крутите здесь уголочки, и вы получите любое ортогональное преобразование, какое только может быть. Но, к сожалению, это не быстрый алгоритм. Вычислительные затраты точно такие, если вы будете по правилу строка на столбец действовать на вектор. В цифровой обработке сигналов впервые многопараметрические преобразования появились в книжечке Эндрюса «Компьютерные технологии в обработке изображений». Старшее поколение помнит, эта книжечка была переведена на русский язык, тоненькая такая, в мягких корочках, и мы ее страшно любили. Володя, помнишь? Нет? Ну, она у меня до сих пор лежит. Он обратил внимание на следующее, что преобразование Уолша – это тензорное преобразование вот таких вот матриц. 1, 1, 1, минус 1. Матриц, самых маленьких матриц Уолша. И он сказал, давайте эти матрицы заменим на матрицы вращения. В результате вместо F2 получается 2 на 2 матрицы Якоби с n параметрами, многопараметрическая. Сказал, ребята, да тут куча преобразований и так далее. Так все это и повисло в воздухе. Я не видел ни одной работы по цифровой обработке изображений 70-го года, где как где-то что-то такое было использовано. Ну вот это Уолш-тензорное произведение, получается матрица из единичек и минус единичек, вот они все здесь. А когда вы подставите матрицы вращения, здесь будет произведение вместо единиц 3 косинусов, вместо минус единиц там косинусы и синусы. Вот граф быстрого преобразования у Уолша. Студенты, это стандартное задание студентам написать программу быстрого преобразования Уолша. Мы берем все эти блоки баттерфляя, заменяем на баттерфляй, классический баттерфляй Якоби. Получается много параметров. А? Потом. Далее, в 80-м году наши коллеги из Ленинградского электротехнического института, Канатов, Солодовников, Спиваковский обратили внимание, что матрица Якоби есть частный случай матрицы преобразования вот такого вот типа. Ну и сказали, давайте в матрицу Якоби заменим вот этой трехпараметрической матрицей. В результате у вас тор становится 3 логарифм двоичный n вот такой размерности. Если n равняется 1024, то размерность равняется 30. Не очень сток большой, где прячутся эти самые ключи нашей ОФДМС. Вот быстрое преобразование Канатова, Солодовникова, Спиваковского. Так, быстрое преобразование Фурье. Очень похоже на быстрое преобразование Уолша, но единственное, между вот этими матрицами Баттерфляй находятся диагональные матрицы с комплексными числами. Комплексные числа, и они, так сказать, обеспечивают получение матрицы не состоящей из единичек и минус единичек, а комплексные гармоники получаются. Но сразу возникает идея, давайте сюда поставим что? Матрицы Якоби. Работа простая, ну просто одно удовольствие делать. Здесь мы поставим экспоненты с произвольными фазами. И у нас за счет этих диагональных матриц количество параметров резко увеличивается. Вот это и сделано. Многопараметрическое преобразование, вон уже сколько много параметров. Уже сток становится побольше, помощнее, и противнику искать ключ становится все сложнее и сложнее. Вот оно, многопараметрическое преобразование, Фурье подобное. Скажем, если размерность преобразования 1024, то размерность параметров уже 15360. Значит, это 15-тысячмерное тороидальное пространство, по которому нужно бегать и искать ключ. Задача чрезвычайно трудная. Есть. Вевлет преобразование тоже быстрое. Ну вот выражение, да, для Вевлет преобразования. Здесь самое главное так называемая masse function, или всплеск у нас говорят, или Вевлет функция, или волнушка. Ну, в зависимости от компании, от коллектива, который работает, название варьирует. Значит, два здесь параметра: сдвиг и масштаб. Сдвиг и масштаб. Если вы будете делать дискретное, интеграл нужно что? Заменить на сумму. Вот дискретное преобразование Хара – это простейший тип Вевлет преобразования. Masse function – вот такой прямоугольный импульс, плюс 1, минус 1. Это усредняющая функция. А дальше масштаб меняется в 2 раза. В 2 раза сжали, парочку таких мазы-функций поставили. В 4 раза сжали еще. Ну и теперь типы. Быстро пробегаю. Все более или менее известные вевлет-преобразования зависят от того, какая вевлет-функция, какой всплеск, какая волнушка используется. Вот они. Хар, Коэфлет, Мейер, Гаусиан, Мексикан Хед, Морлет и так далее, и так далее. Ну и широкий класс предложила Ингрид Дёбиши, и целый класс вевлет-преобразования называется вевлет-преобразование Дёбиши. Эти вевлет-преобразования зависят от 2 наборов коэффициентов. H-коэффициент и G. Это усредняющие коэффициенты, это дифференцирующие. Это название в кавычки можете взять. Но на самом деле от одного набора коэффициентов, потому что дифференцирующие вот по такому закону выбираются. Оказывается, любое вевлет-преобразование можно представить в виде произведения слабо заполненных вот таких вот матриц, как я говорю, лестничного типа. Вот одна лесенка, H, здесь коэффициенты усредняющие. Следующая лесенка, красная лесенка, а это дифференцирующие коэффициенты. Они циклически сдвигаются. Вот на 2 позиции сдвинули, и хвостик вылез вот сюда, циклически. То есть это лестница винтового, так сказать, типа. Ну и все они ортогональные. Но коэффициентов-то не n. Например, если это размер 1024, а тут всего 3 коэффициента. Матрица ортогональная. Значит, если я к этой матрице применю алгоритм Якоби, пытаясь обнулить хвост, следующий хвост, то я получу маленькое количество матриц вращения. Эта процедура была нами и использована. Ну, это блок алгоритма. Беру опять ту же матрицу Якоби и начинаю вращать. Вот сначала строки переставляю с тем, чтобы вот эти вот 4 были одинаковые. 2 раза толще панели у лестниц делаю у лестниц. Вот одинаковые. И эти пытаюсь обнулить. Вот этот элемент, это 6 коэффициентов. Пытаюсь их обнулить. Плохо, наверное, здесь видно, но вот здесь беленькие плюсики стоят. 6 коэффициентов. Я пытаюсь один обнулить. На самом деле свойства таковы, что обнуляется сразу парочка. Но обнуляется не только хвост у этой строки, но и обнуляется голова у этой строки. То есть попытка обнулить один элемент приводит к обнулению сразу 4. Это свойство Дёбиши. Ну и в результате у меня было что? 6 коэффициентов, стало 4 коэффициента, потом стало 2 коэффициента, и, наконец, получилась перестановочная матрица. И я матрицу лестничного типа представил в виде произведения матриц вращения. Сразу. Вот быстрый алгоритм. Уголочки меняете, и оказалось, вы все вевлет-преобразования, которые придумала Дёбиши, вы накроете при изменении параметров. Итак, как в радиоприемнике есть ручки для настройки частоты и так далее, так и в этом преобразовании есть столько ручек, сколько параметров. Меняете и настраиваетесь на любое вевлет-преобразование, которое только придумала и не успела придумать Ингрид Дёбиши. 16-точечная и так далее, и так далее. Вевлет всплески какого типа при изменении параметров? Внизу параметры двухпараметрическая. Вот это mass function, это фаза, это mass function и так далее. Вы видите, что эти всплески имеют в некоторых случаях чисто детерминированный характер. Ну, например, вот он, это хар. То есть классический ХР, вевлет преобразование, хар. Чуть-чуть изменил, и у меня что получается? дифференцирующая функция, wavelet функция, носит хаотический характер. Эти функции я и хочу использовать в качестве поднесущих. Но представляете себе, какая трудная задача перед средствами радиотехнической разведки стоит, чтобы определить вот эту вот функцию, эту поднесущую. Гармонический сигнал имеет простую вот такую форму, а эту даже и описать-то нельзя. То есть поднесущие становятся хаотическими, случайными сигналами, и средством радиотехнической разведки определить становится чрезвычайно трудно определить внутреннюю структуру поднесущих. Ну, еще куча примеров. Как видите, и вот здесь при некоторых, ну, чисто хаотический характер. Здесь детерминированный, здесь вот, ну, очень похоже на Mexican Head. Ну, чуть-чуть деформировано, по шапке кто-то дал кулаком, она, всплеск, wavelet функция деформировалась. Здесь хаотический характер. Короче говоря, ну, здесь экзешник, я бы показал, как меняется форма. Но мы использовали это многопараметрическое преобразование, небольшое отступление для сжатия данных. Для сжатия данных возникает вопрос, а как выбрать параметры с тем, чтобы коэффициент сжатия у компрессора был максимально возможным. Для этого нужно что? Чтобы у спектральных коэффициентов гистограмма была как можно уже. Тогда энтропия спектра будет маленькая, а энтропия впрямую связана с количеством бит, которые необходимы для кодирования этого изображения. Вот мы нашли, взяли, прогнали во всем диапазоне два параметра и посмотрели, где энтропия принимает минимальные значения. Минимальные значения. Вот она построенная функция, двухмерная. Видите, есть глобальные минимумы и локальные минимумы. Вот этот локальный минимум совпадает с преобразованием Дюбюши. Остальные все минимумы соответствуют тем wavelet преобразованиям, о которых Ингрид Дюбюши даже и не подозревает. Многопараметрические преобразования Галлея. На прошлой конференции я рассказывал этот фрагмент, я его пропускаю, потому что идею, как мне кажется, я до аудитории донес. Что нужно делать? Это тоже реализация комплементарных последовательностей. Пара, вот, например, функций, у них спектр такой, что, складывая спектр одной функции и второй, получается константа. Или сумма автокорреляционных функций этой и этой равняется дельта-функции. Это комплементарные последовательности. Ну и теперь еще очень интересный класс, и переходим к сути дела. Многопараметрические Фурье преобразования, которые обобщают дробное преобразование Фурье. Ну, любое ортогональное преобразование можно диагонализировать. Это стандартная задача из линейной алгебры. Q и Q матрица собственных векторов. Преобразования U на диагонали стоят собственные числа этого преобразования. Находим вторую степень произведения вот в этой форме. Q-1 и Q аннигилируют, уничтожаются, появляется единичная матрица. В результате собственные числа возводятся в квадрат. Значит, если я ортогональное преобразование возвожу в квадрат, то собственные числа возводятся в квадрат. Если я возвожу ортогональное преобразование в n-ную степень, то собственные числа возводятся в n-ную степень. Ну, а тогда я могу вместо целочисленного n взять любое вещественное число а. И в результате получится однопараметрическое преобразование U. От одного параметра оно зависит. И эта идея была в 80-х годах в квантовой механике предложена для получения так называемого дробного преобразования Фурье. Итак, преобразование Фурье, вот матрица, ее матричные элементы диагонализируются. Q и Q минус 1 – это дискретные собственные вектора, это дискретные функции Эрмита. Дискретные функции Эрмита здесь сидят. Собственные значения могут принимать только 4 значения. 1 йод минус 1 йод. Поэтому я возвожу в степень, и собственные значения возводятся в степень А. Но здесь есть некоторый нюанс, связанный с преобразованием Фурье. Если вы будете последовательно возводить его в степень, то 4-я степень преобразования Фурье превращается в тождественное единичное преобразование. Тождественное. Значит, степень не может быть выше 4. А на самом деле она меняется по модулю 4. Значит, А может меняться от 0 до 4. Ну вот в это выражение 7 минут в моем распоряжении. Как я? Уже 6. Хорошо, я успею. Спасибо. Значит, если я небольшие преобразования сделаю, эту 4 поднесу под А, то А нормируется и будет меняться новое от 0 до единицы. От 0 до единицы. И тогда я вижу, что нормированная А – это есть доля от 2π. Доля от 2π, то есть доля от окружности. Доля от окружности. Поэтому если в качестве степени использовать А нормированная, то получается дробная, потому что А от 0 до единицы, там дробные числа. Ну а теперь следующий шаг вы сами спокойно сделаете после того, что я вам рассказал. А почему мы должны собственные числа возводить в одну и ту же степень? Каждое собственное число можно возвести в свою степень. Тогда получается n параметров. Это называется многопараметрическое преобразование Фурье. Я покидаю все эти, спектры покажу. Вот, например, прямоугольный импульс. А равняется нулю. Дробное преобразование превращается в тождественное. Любое преобразование в нулевой степени – это есть что? Тождественное преобразование. Вот А равняется нулю, прямоугольный импульс. Начинаю менять параметр. Бежит до единицы. Спектр при А равном единице дробное преобразование Фурье превращается в обычное Фурье. F в первой степени – это и есть F. Спектр прямоугольного импульса – синус x на x. Но 0 частотный вот здесь находится. На самом деле вот эту и эту надо соединить грани. В тор превратить. Получается синус x на x. Следующий спектр, который вы знаете, дельта-импульс. У дельта-импульса энергетический спектр какой? Константа. Константа. Вон она, константа, и на заднем плане и имеет место быть. Куча других спектров. Треугольный импульс. У треугольного импульса энергетический спектр синус x, деленное на x в квадрате. Вот он здесь и есть. Боковые и главный лепесток здесь есть. Все. Противоподслушивающие свойства. Я уже практически рассказал. Единственное, что нужно показать графики. Сколько? 1 минута. Итак, 2 легитимных пользователя. Алиса и Боб обмениваются информацией. Ева пытается подслушать. Алиса и Ева работают на рабочем параметре с фиксированными значениями параметров. Ева с помощью своих средств радиоэлектронной разведки определяет структуру ортогонального преобразования, находит ключ, включает и начинает подслушивать. Но эти тоже не дурачки, они берут и изменяют значение параметров, переходят к другому ортогональному преобразованию, Покажу график и на этом заканчиваю. Я вас вижу.
Couple of minutes for questions, please. Both languages are accepted. Excuse me, your question should be addressed to everybody. Could you use microphone, please? Microphone. Можно микрофон увидеть?
Все, комплексы.
Okay. Other questions? Yes, please. But please use microphone. please use microphone because people won't hear you.
В начале доклада вы приводили примеры преобразования Фурье, Уолша, Хартли, и просто сказали, что все это дело проходит, вся эта техника для М-преобразований. Ну там же быстрых алгоритмов-то нет, что там.
Для каких?
М-преобразование у вас было написано.
Не, в М-преобразовании быстрый алгоритм есть, он хорошо известен. Если вы переставите строки матрицы М-преобразования соответствующим образом, то столбцы примут форму преобразования Уолша.
Ну, значит, мы просто разные имеем в виду М-преобразование.
Ну,
в видимости, у нас терминологическое какое-то.
те, которые генерируются
М-последовательности.
Да, М-последовательности, они все, любые, бинарные, они имеют быстрые алгоритмы.
Spasibo.
Okay, thank you very much. And, it's a pleasure for me to, you can just prepare your slides. And it's a pleasure for me to introduce our next speaker, Professor Michael Sobolewski, who is a world-class scientist in Air Force Research Laboratory, Aerospace System Directorate, and professor at the Polish-Japanese Institute of IT, Warsaw, Poland. He has over 100 publications in journal conference and books in the area of distributed computing. He has served as a visiting professor, lecturer, and consultant in many, many countries, including Russia. Professor Sobolewski, the floor is yours. Welcome.
Good morning. Thanks for the introduction. Today I'm planning to tell you about service-oriented governance with service programming language. What is governance? In general, governance is the set of rules and laws framed by the government in politics that are to be implemented through the representative of the state. Simply put, governance is what governments do, basically, okay? So, in service-oriented computing, governance is service-oriented process expression, and as you know, the computer science is the science of process expression. So, if we talk about service-oriented computing, we assume that everything is service, like in object-oriented programming, everything is object, like in procedural programming, everything is procedure. As in functional, everything is a function. So normally you cannot find formal definition what is service, and basically there is no really service-oriented systems except what I'm doing over past 20 years in many different organizations. And government, in the context of regular concept of governance, is service-oriented process actualization, which is normally in computing operating system. And representatives of the states correspond to service-oriented processor, which is in service-oriented computing, is the network of services. So all services in service-oriented computing are not available directly, because if they are available, they have static connections, network will break. There is no network really, it never will be completely secure and reliable. Because of non-reliable network, if you want to have reliable service-oriented computing, you need non-direct communication. That means consumer of service never talks directly to the service provider. And it is really difficult to achieve. And that's one of the major problems why service-oriented computing is not widely used yet. So service governance is defined by rules and patterns of service composition and an execution platform. And I'm talking already for a long time about Sorcerer, and Sorcerer is like, you know, any other good programming environments like Java. When you say Java, for some it is just coffee, okay? But for some it is object-oriented platform. for some, within that platform, they don't think about platform, but when you hear Java, I do Java program, this language basically, okay? And Java itself is operating system. Operating system that uses basically virtual machine with own file system, all virtual machine modules and so on. And obviously Java is also philosophy. It is object-oriented philosophy. And the same we do basically with Sorcerer. When you hear Sorcerer, it is service-oriented computing environment. My colleagues at General Electric Research and Development Center came up with that idea. By the way, yeah, I teach only in Polish-Japanese Academy of Sciences once per year for 1 week, and the rest time I work in the States. And initially I came for 1-2 years. I'm already working for 30 years, so I am almost all the time there. So, in Sorcerer is philosophy, it is computing platform. It has language, service modeling language, it has obviously network operating system. And usually when I talk about Sorcerer, I talk about one of those components. And today I'm trying to basically talk about service modeling, service-oriented mogramming language. You tell mogramming, you will soon learn why we are talking, but mogram is either model or program or any combination of models and programs or anything else, okay? In the past, we assumed that model is conceptual definition which is not executive. Currently, we run models basically as executive entities, and usually model is declarative while program is imperative, okay? That's the reason in service, when you create governance all computing paradigms, and that's the reason we use a term mogram, and language is mogramming language. So why you need service governance? First of all, it is not a buzzword for doing computer client-server computing or any web services, okay? We tried that for many years. When I came to the States in 1989, we worked on $100 million project funded by DARPA, DICE, DARPA Initiative in Concurrent Engineering. I have some data here. We tried basically to do service-oriented computing 30 years ago. And as I told you, $100 million project. And it was to some extent successful. We applied to G90, the General Electric engine that runs on Boeing 777. Okay. Then basically I work on FIPER. That was my project for $21.5 million, Federated Intelligent Product Environment, that was funded by NIST, National Institute of Standard and Technology, to develop service-oriented technology. And then I continued basically research at Sorcerer, where General Electric founded the laboratory for service-oriented computing, Texas Tech. And during 8 years, we developed basically operating system that Air Force Research Lab started using in production for designing new generation of air vehicles. And as I told you, I teach basically service-oriented computing systems and software engineering design to create service-oriented computing system. And here basically, not everyone needs service-oriented computing. Service-oriented computing is for large, complex, adaptive system where you do computation or design with millions of billions of variables, okay? And you have to do this on the network. You use basically all computing resources in the network, supercomputers, clusters, workstations, because the number of variables is huge and the processing power is enormous, because you don't want to design, let's say, geometry and make a plane. You want to fly that plane virtually and check all parameters during flight virtually before we'll go and start making a plane, because I don't have the slide, but that is interesting slide. DARPA asked for research. why planes like Osprey or F-35 are basically from original design to introduction into practical theater. It takes 25, 26 years designing a plane that it is used. There's enormous amount of money, and the government said no more money. You have to do basically design using high fidelity physics. Because why they do design so long? Because those planes break. Because if you use those empirical formulas for designing, they have error up to 20, 30%. And when you design, then you fly and it breaks, it breaks, it breaks, it breaks. So they started introducing high fidelity physics model, but that's huge compute power basically. And basically appropriate languages are needed. So that's, and oh, I forgot to mention, a year ago I was talking here about Sorcerer, but in the context of emergent, that was the title of my presentation, emergent multi-fidelity service system. Basically, we are looking, the topic was basically on the issue that if you run computing and basically optimization of very complex system, you want to observe emergent behavior and acquisite knowledge, learn and build new theories about how to build a thing that you are really optimizing, okay? So it is basically a kind of knowledge acquisition in very large systems. But today I want to be focused more on language, which is process expression. And as you know, there are many ways to express processes, and there are many different types of processes. When I was here, many presentations have been talking about only algorithms. Algorithms is very narrow class of process expressions. Okay, most processes are not algorithms, just my comment. And service-oriented computing is not algorithmic. You might use algorithms, but in general it is not. Object-oriented programming is not algorithmic unless you use object-oriented programming only for procedural programming, which is, in most cases, people are not aware what is object-oriented programming. They use object-oriented programming languages, but they write algorithms, basically. So this is the summary, basically. So you have basically domain. You want to create basically different types of analysis. You have to express those processes, for example, design processes, optimization processes, exploration processes, parametric analysis, and so on. And basically, you don't want to do this in software languages because the number of programs already written is thousands, okay? And which program to use when it is not clear and it is not easy. So engineers don't do this normally because that stuff is written mostly by programmers, software developers. So the concept here that you use basically executive codes that can run on many different platforms in the network, really. And you have operating system that basically uses domain-specific languages like service programming language. I will show you how it looks basically later. And basically operating system allows you to use executive codes as basically service avatars. I hope everyone has seen the movie Avatar. So basic codes that everything we write in software engineering becomes software avatars for softwares which are used here. So software is programming language for governance is not really executive code. It is called governance. It basically specifies how to use executive codes. Okay? So, and this is part of the, it is just language, the new term used in computer science, language engineering. So I am focused basically on language engineering for service orientation. And that's basically where it is applied. You have a lot of new concepts like we need in programming a discipline, we need in programming couplings between disciplines, we need in programming multi-fidelities as first-class citizens. Not using some objects, but you have those domains more in service sense, functions which bind to those service avatars code somewhere in the network. That was what I was trying to explain a year ago, basically. So I will skip this, that emergent behavior with multi-fidelity managers, which is a really powerful environment to basically acquire knowledge and form automatically new theories about design. And that's what I'm trying to emphasize today, that we are already for a long time in service economy, and the change really is reinforced by economy. So if you look here at the picture, today's services sector makes up to 80% of US economy. 80% that service. Companies like General Electric, even when I joined in 2002, General Electric Research and Development Center, at that moment, General Electric was making 50% money from services. But before it's completely manufacturing company, okay? So you see that increase is 500% in services currently, basically. So, and manufacturing is decreasing. So the value of products decreases, and we move basically into services. Why that happens, basically? It is related what is called in economy product dominant logic, where production is the core of value creation process. So you have basically producers, and the value is in the production. You want to basically produce as much as possible, possibly mass production, as cheap as possible, and distribute to customers. And with that idea came, as you know, Ford with Model T, and he was assuming that if you will produce cheaper cars, everyone can buy, and market will be running forever. But currently, markets are saturated with products. It is not so easy to sell products, and what economy is doing? Creating services for those products. That's the reason we have a service economy where the focus is shifted to services, okay? And that's the second part. So this is the standard process. Also in software engineering, we are changing, and we want to do what is economy already doing, basically. We try to, all those business like General Electric, when I worked, they try basically to provision those products and make services. Like General Electric, I don't know if you know, makes aircraft engines, but they are not selling engines. They have GE Capital, and GE Capital takes those engines and leases those engines, basically a service. So they get money, really not selling engines, but providing services. Engine becomes as a service, okay, like a car. If you look in the car is just avatar, physical representation of the service, which is really service of moving us from A to B. That's the reason, you know, like in New York City, it doesn't make sense a car at all, because for parking, you pay per year more than value of the car, okay? And on the top, you have to pay insurance, you have to pay for maintenance, you have to pay for gas. But doesn't make sense, basically, to use product as customer, because other services related to car are so expensive with respect to car that it doesn't make sense. What happens? You know, Uber, okay? And you have that possibility. You take iPhone, basically, you click on Uber, that's a service. Uber uses mapping service. You have a map, you have GPS, okay? And then basically, you have cars displayed. You point where you want to go. You have car displayed as basically basically avatar, okay? And then you select the car, and car comes, and you pay for a ride, okay? And you know probably that Uber is investing heavily in the States in self-driving cars, So they would need, even in the future, no drivers would be needed. And cars go away as a product they will be buying. That's the service economy. And the same, we apply already, we started applying, that was the concept basically, because service economy, software development. We want to use software basically as basically a product. That means we want to basically, this is current predominant software development process. You have software development process and you create software artifacts, executed codes, which are products. And you basically sell, distribute to customer. But in service-oriented computing, we don't use term customer because those products are custom products that user cannot change. So we want basically design, for example, designers who design plane or design any very complex system with high physics, basically physical, with models based on high fidelity physics. They basically use a lot of the ATUs, application tool utilities, okay? This is the avatar of the services, physical representation, what they want to use here, but how to connect and use them, engineers know very well. They don't have currently tools, possibility to integrate hundreds of thousands executed codes into a code, because normally that integration is done by producer. I jumped too quickly. Anyhow, so basically in service-oriented computing, the consumer basically is co-producer of the, let's say, product, because it uses own knowledge, and the value in service-oriented computing shifts from the production process to the basically co-production by the end user. End user is becoming co-producer in terms of application tool and utilities so spread and used in many ways. Like when I started working on 5P project, General Electric aircraft engines, they had 30,000 programs, okay? And they know what best tools are for what processes, and they would like to eventually, in uniform way, to create service governance, how to govern those executive codes, application tool utilities in the network, including basically provisioning. Provisioning is the toughest part, basically. That's the reason in fact have taken us so much time, because those application tools and utilities, they are not in the network all the time. When you create your governance, the governance includes deployment. So they are provisioned on demand when they are needed in the network. You finish your computing, they disappear from the network. So they are not servers. And that's an illustration also that we are moving from few node systems, like those are servers, and they have static connection. One server will die, the whole system dies, okay? And when you go to complex really computing, that's really never works. So in service-oriented basically computing, we have a lot of lower granularity than here in client-server computing, and the value is on the connectivity, okay? Many system dynamics largely result from interactions among systems. Those interactions really are defined by governance. That's what we say. We govern, we create the federation of federations, really. So for that, we need high-level languages, and that's a kind of summary, basically. So software engineering is focused basically on creating executive codes and objects. That's software engineering. In service-oriented computing, provisioning basically moves those executed codes and objects to service providers. Service providers basically are service avatars. Those are not really avatars. So avatar, physical representation, service-oriented computing are service provider and evaluator, and those are network containers then eventually run those objects inside in the network. And you are not maintaining any direct connections to those elements. You will find them only by type, by service type, which is unusual, and people don't know really often how to do this. And then you have governance on the top. So governance, basically in the language you will see we use, doesn't have anything directly connecting to object codes or even to service providers. Service provider just expose service type, multi-service type, we call this multi-typing. Where a multi-type, you will find instance in the network. If it doesn't exist, that instance is provisioned, and you can basically refer to that instance in governance, what to do with that service. We want, as I mentioned here, so we want to compose executable codes and objects in service network using programming languages with various programming paradigms. So we decided that basically different people have different preferences, and this is basically the choice of the user, consumer that consumes services. The name consumer consumes services. It is not customer that uses custom for him or her design program. And so we just specified basically, it is also for design the language, what is called demogramming gate. And those are basically basic three existing programming paradigms. Those are basically pillars for each paradigm. This is basically domain, usually data, control strategy, and composition. And composition, control strategies, and data is differently used in each paradigm that you have to know if you are really working in computer science, because I told you computer science is the science of process expression, and those are functional processes, those are algorithmic processes, those are object-oriented processes, and we are talking in Sorcerer in service-oriented processes, and they are based basically on those pillars: contexting, multi-fidelity, and multi-typing. Multi-typing, I mentioned, it is just to compose service federation in the language. Multi-fidelity is real control strategy, and contexting is basically the independence of individual parameters, so service can work with any data in general, okay? So contexting really, by the way, everything is what we use contexting. That means it has ontology. So we maintain ontology for data in the network, we maintain ontology for services, how to find them, and multi-typing is basically one of many possible fidelities because the approach is to have a system of systems. And by changing fidelity, you can move from one system to another. So when we do optimization, you are not optimizing a particular one system. You are optimizing, but during optimization, you create via emergent properties new system. So basically, you look for the best system and find optimal solution of the system that you haven't defined. Because multi-fidelities, they have different range, but you can change all fidelities in the system. That means it is computing completely differently than before. It is different system. So you have like basically a large number of systems in the same program. So obviously, when you look now in the internet that you are using, probably nobody of you believes that internet will survive so long. We need basically the intelligence in the network, and that's the problem with using service-oriented computing, because you need the intelligence in the network. If you don't rely on static connections, how you find your services in the network? You need intelligence, ontologies, I mentioned before, to find basically in the network. Because of that, but the current network basically is called dumb network with respect to what we want really. And in dumb network, basically, it was designed for simplicity inside. You have routers basically, but the assumption was the intelligence lives at the ends, which is end user has everything is the whole intelligence at the end user and the other end. You are connecting via static connection. And basically, in DAM network, we just deliver bits. That's DAM. The data will tell you the network where to go, the data at end, basically. And that's what is called the end of the end principles. And basically, that implies, probably you've heard about 8 fallacies of distributed computing. So if people are not aware about this, because they assume that everything what is true in computing on one platform will work when you use the network. Always fails, and that's the primary reason why service-oriented computing doesn't move, because people don't know how to create intelligence in the network. And I will go faster, but I will tell you that basically the issue is if you have that service avatar, how to make presence or even provisioning in the network. Do you remember? I told you that when we move from manufacturing to service orientation or service economy, the first element is how to provision services. Who will be selling those services in economy? Here, who will be providing those executive codes, objects to you? That's basically service provider, but you cannot talk directly to the service provider, which is not possible with this type of network. That's a kind of graphical illustration of what I was talking. So you create basically the consumer governance, and you will see how we do in service modeling language. It is very simple language, frankly speaking, but the infrastructure and that network intelligence is needed because you operate in global network and the operating system exists in the network. So this is the major intelligence, how basically a provider starts, which is the avatar for the service, how it registers with registers in the network. You don't know where those registers are. There are special basically discovery joining protocols. They do not exist in any type of services. And we were basically on that with Sun Microsystem, which is gone now. Oracle bought Sun Microsystem. It was at the time we developed together for FIPA project, and it was called Genie technology. And currently it is Apache project called River. So if anyone would like to understand how to put intelligence into network, you have to be familiar with River project. And nobody teaches that. I was teaching in my lab at Texas State University. That's the reason it was possible for me to create a group of 28 PhDs who basically worked with me to create the technology. And so this is the operating system services. So kernel and consists of services in the network. They are replicated, usually up to 5. So with 5 services in the network, you have 99 and 9 nines that one always exists in the network. And governance, basically you specify what you want. With help of operating system, creates those services, user-defined service federation. And everything runs in those service providers that provision services available at the language level. So that's the concept. And how we have done this, you can define languages in 2 ways, using grammar or meta-modeling. And I had the opportunity to work to represent General Electric for 5 years at the technical committee of OMG, Object Management Group, the group that was designed basically UML. And most people don't know, but UML has meta-modeling hierarchy. This is meta-object facility, then there is UML, then you create your model in UML, and then you have runtime, basically, object model at runtime. And this is the avatar for Sorcerer language that has the same hierarchy. We have meta-service facility, service modeling language that I'm presenting today, basically. Those governance is really a mogram. We have, a mogram is generic term for service-oriented program. Governance is one type of programming for for federation, really, for federating those services. And then that program basically, with help of operating system, basically bounds to creates the federation, and that federation is just source of runtime collection of objects running in the network, okay? So that was really GE technology we use here, and for provisioning another open source project, and sources is also open source project, but only one level. We have like 4 levels used at Air Force Research Lab, so only the bottom is available. The rest is not available. So that's the part basically we have developed over years by analogy to UML. And only that UML is graphical and SML is just functional language. So how, and that's the semantics. That's really, you know, was very difficult over years how to explain to others what is service, and basically finally we got, I don't know, like in past 2 years, the full semantics uniquely specified. So as I told you, this is process expression. That's really what is called services science. That stuff here is called really services engineering. And basically that's here is service software engineering. Basically you write those codes which are provided by service providers. So because it is service-oriented environment, everything is service. So the program that you create, governance is also service. We call them request services. There are operation services, there are elementary services, there are federated services. That's what end user creates, basically, and runs as a federation of providers. And the 2 operation services, you will see in a moment how they look. Signature and evaluator, and signature has multi-type. That multi-type basically is a service type or service provider, which is a collection of multi-types of service interface types. As you know, all object-oriented languages have service types. Java has basically service type, which is basically interface to classes that have to implement it. So obviously you need to use the service type, but there is no IP addresses, there is no protocols. That is called sometimes technology that says the end of protocols, network protocols. User doesn't need to know about protocols, nothing. Okay. I don't have time to go into details, so let's go. Basically, this is from tutorial exam. Basic, like you have hello world, you have service-oriented hello arithmetic. So you have, oh my gosh, what I did, backward. So you have basically, it is block structured here programming, like you know, in procedural programming, you have basically block in block. This is basically the data. Which provide the scope for inner block, and in that inner block we have another block. So that's the state of all blocks. And basically we have here 3 services: multiply, plus, minus. Okay, and we assume that there are executed codes. You can just think that plus, multiply, minus is any tool in the network. Okay, they're just, you know, explanation. And basically you want to create the governance to run the computation, which is here specified in a kind of procedural way. Okay, so that's the program in Sorcerer that you can execute. Okay, you specify basically the tags, this is the name, and that's the signature. And you say, signature, you put the name, if, that's the operation. That's the operator selector, and that's the interface. That's it, okay? And that interface, as you see, I use here the class implementation. If it is, Sorcerer allows you to build monolithic program that runs on one computer at any time, distribute any service, like here in that case, task is a service, automatically into the network. Okay, the concept is based on the differences I told you between class and interface. So if in signature you specify class type, Sorcerer will create instance for you at runtime to use. Okay, If you specify interface, Sorcerer will find or provision that service avatar in the network, okay, the provider. You don't need to know where those services are, if they are in the network or not, what computer is used. You can specify you can add to signature deployment descriptor, it will deploy on the right computer, like supercomputer or cluster or workstation, okay, automatically. So we specify basically 3 services. Those are tasks, and we create the block. Okay, we create block that means do service T4, T5, which is multiply and add. Okay, and then in that block we have outer block, subtract, basically another service from the service. Yeah, okay. Yeah, so this is just basically using a block. We call this block governance. Block has inside the block. We have here not block but job. That's another governance. This is workflow. So block is basically procedural programming. You have basically branching and looping blocks. So we have full algorithmic logic with blocks, like procedural programming. I told you all paradigms we want to have with services. You create a job, which is like workflow. And here also you have job, inside you have another job. It is the same task, but represented as a workflow, okay? You can do the same as a model. Here I use just basic expression. All those, as you see, run in Sorcerer, and really you can execute them in the tutorial that comes with Sorcerer. Here we use basically as a model. Model is basically a kind of functional programming. Okay, this is you use really functional programming just using lambda expressions, and you can mix and match all that stuff any way you want. And this is more interesting. This is the Solar model. This is the optimization. You know, as a tutorial again called Solar model. By the way, it was first time solved in 1996. It is optimization problem. You have like, it looks like, you know, classical definition, but it has 2 domains. Y depends on Y2 and Y2 depends on Y2 depends on Y1. So you have coupling between those disciplines. So we have one entity discipline, the second discipline, and we have, it is the simplest multidisciplinary problem, and you want to solve that problem, okay? So in Sorcerer, you specify basically, it is my colleagues decided to call this operator MADO, multidiscipline analysis and design optimization model. Basically, you specify objectives vars, output vars, input vars, constraints, basically, and you have basically 2 disciplines. Basically, you specify couplings, you add sensitivities, it is gradient bands, you run this, and you get optimal solution. Okay, how you do this? You have to specify basically the data, which is context. This is what I told you, we treat context as a kind of ontology. And even in the context, you specify how to run MDA. And MDA here is specified by basically lambda or by a class that implements basically the MDA interface. That's it. So you need the data for that model to be optimized. You need also the task. Like before, only the task specified in the context what is optimizer, what is strategy, and so on. And we run basically and check the results of the optimization. Now those 3 elements you can put together, and basically, yeah, those are morphers. You don't have time. But at least service discipline. Service discipline is like model view controller. You specify multi-fidelities for governance, dispatcher, and context. Model is governance, by the way, that I showed you for Solar model. Yeah, okay. And dispatcher basically is a task. Context, you put those together and you create basically this. So this is the discipline. And basically you can execute discipline as one task, basically. So what, that's the time to summarize. So I would like to that you will take away 3 points. Multi-fidelity service oriented semantics, because each request has multi-fidelities, okay? Multi-fidelities are everywhere in the system because multi-fidelity is ad hoc polymorphism, so it allows you basically to adapt the system any way you want. In order to do this, you have morphers associated with fidelities, and morpher watches what is input-output, and then runtime changes fidelity. So you can go from fast execution, not precise, to high fidelity model when it is really needed. And yeah, those are basically, those are types of basically transroutine, transmodel, and transdiscipline. Those are 3 patterns for governance. And that's the illustration, basically, what is federation or collaboration. If you have just elementary services, that's basically is collaboration. But if you use a hierarchy of governances, this is governance, 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 those are collaborations. So you have basically here service federation that comprises from 6 collaboration and 4 federated governances. So federation is like federated government, like in the States, for example. Okay, each state has own. So let's see, those are states that have own governance, basically. And you can build very hierarchy with, let's say, hundreds or thousands of services in the network. The issue is scalability also for, you know, large-scale system. I'm done. Thank you.
Great. Thank you very much. We have time for one very quick question. No questions? Then we will thank Professor Sobolewski. And the next, how should I pronounce your surname? Medio, yeah? Okay. And it's a pleasure for me to, could everybody settle, please? And it's a pleasure for me to introduce our next speaker, Dr. Alberto Di Meglio, who is head of CERN Open Lab. Alberto has an extensive experience in design, development, and deployment for both commercial and research applications of distributed computing infrastructures and software services. So, Alberto, the floor is yours.
Thank you very much. Good morning. It's a pleasure to be here. I have a lot of things to say, and since our chairman today looks very strict, I need to, to manage my time correctly. So, yeah, my name is Alberto Di Meglio. I come from CERN. I'm the head of this unit at CERN called the CERN Open Lab. And what I would like to talk to you about today is really a high-level overview of the major challenges and opportunities in data-driven, data-intensive scientific research, taking, of course, the high-energy physics domain as a starting example. So I will show you a number of examples, and please, I would like you to consider these presentations also as an opportunity for further discussions and collaboration. I'm going to touch upon a number of interesting, in my opinion, directions or areas of research on which there is a lot of work to do. So again, it's all about collaboration. So let me start with my one slide history of science. Of course, I'm sure you know all about this, but just to set the context. So, of course, for many, many years, scientific research has been all about empirical observations and interpretation of natural phenomena according to the particular thinking of philosophers and scientists in particular moments of time. This has gone on for many thousands of years until about 500 years ago, where the formal reproducible experimental method and the first mathematization of science started, Galileo Galilei, for example. And this produced the outstanding advances in science in the last few centuries, the theory of gravitation, electromagnetism, thermodynamics, quantum dynamics, relativity, and so on. until about 50 years ago, when the computers started being used for science as well, and then all the mathematical models becoming very, very complex to solve in exact terms were solved numerically with the computers, producing very detailed simulation of this phenomenon. Today, we are in something that it is called the fourth paradigm, is something invented. The term has been invented by Jim Gray, he's a fellow at Microsoft in 2009. And fourth paradigm is a sort of combination of all that. It's very large-scale, data-intensive scientific research where you put together the observation, the theoretical models, the simulation, and the computing to solve very difficult and very important problems of fundamental science. Now, CERN is one of the examples of this kind of model of working. The high energy physics is an international collaboration of thousands of people. CERN itself is a collaboration of 23 different member states and many more observers and collaborators. There are during the year, there are between 13,000 and 15,000 people working at CERN to solve these interesting fundamental physics problems. Now, CERN itself is not about the scientific research. The scientific research, the physics research, is done by the experiments that use CERN, the accelerators at CERN, as an instrument for their research. And this is the accelerator. So let me just very brief information in case you are not familiar with this. But so the yellow line is the current main accelerator. It's a Large Hadron Collider, 27 kilometers in circumference. For comparison, this is Geneva Airport here. The whole of the airport could stay many times inside this circle. And there are many other accelerators that historically have been used for other experiments and today are used as an initial boosting stage for the Large Hadron Collider. So, in the collider, there are two counter-rotating beams of hadrons, heavy particles, so protons or ions, that never touch, so they go in parallel inside the accelerator, and they are moved to hit each other in 4 points, where the 4 main LHC experiments are sitting today. ATLAS, CMS, ALICE, and LHCb. So together, collectively, the raw data produced by the 4 experiments, it's about 1 petabyte per second of data, which is an amount of raw data that with today's technology cannot be processed in real time. It cannot be analyzed. So it would take, just for example, only for storing this, taking standard disks as a comparison, it would mean storing more than a few thousands of these hard disks per second, which is something that, of course, cannot be done. So how to cope with this? What has happened until today is that a lot of this data, about 99% of this raw data, is actually discarded, is rejected, according to a number of simple rules that are encoded inside what is called the standard model of physics today. What is left after this initial processing is then moved into the CERN Computer Center, where the rest of the processing starts. Today, just to give you a few numbers, the CERN Computer Center has almost 300,000 cores for processing cores. Almost a half an exabyte of storage capacity, 35,000 kilometers of fiber optics going around the site. And this represents only around 25% of the entire capacity of the high energy physics community around the world. So what happens after the data is processed initially in the CERN Computer Center, it is then distributed across the world. CERN is called the tier 0, where data is generated, and the other sites are a sort of pyramid structure of distribution of data and computational tasks. Today there are 13 tier 1 centers and a couple of hundreds of tier 2 centers around the world doing this processing. So it's really a very large international collaboration. So this has worked very well until now. The main reason for this until now has been to complete the standard model, find this elusive Higgs boson, and this has been done and officially announced in 2012. And this has sort of concluded the last big missing piece of the standard model. So now we have to move forward. What's next after that? So the problem is that the standard model itself, this classification of particles and interaction, actually describes only 5% of what must exist in the universe for the universe to be as it is. If you look at galaxies, the way they move, the speed of rotation, there must be much more mass producing the actual gravity that exists in the universe. So what is out there? Today, of course, you know about all the discussions about dark matter, dark energy. The term dark means indeed that it is not clear what it is. And there are many open questions about matter and antimatter. Why antimatter doesn't exist in nature, in the universe, in the part of the universe we live in at least. Although it can be created in laboratory, of course. And what is the relationship between the microscopic quantum world and the macroscopic gravitational world? So there are many open questions that until now have not been answered. So what can we do next? So just to give you a general idea of the difficulty. This is searching for the Higgs boson was compared to looking for the proverbial needle in the haystack. Now, that is in general difficult, but it is actually easy because you know what a needle is, you have a definition of the needle, and you know what a haystack is. You have a definition of the haystack. So if you have enough time and enough computing power, you can actually look for something specific and find it. Now, the problem is from now on, this doesn't work anymore. We have to find a needle in the middle of many more needles, and we don't have a precise definition of everything else. So this requires a lot more ingenuity and a lot more innovation to actually solve these problems. And this has an interesting effect on the IT, on the information computing technology part, on computer science and data science. So this line, the blue line here, represents what is called the luminosity of the accelerator. It is essentially a measure of how many particles you can pack, you can put in the cross-section of the beam. So the more particles you have, when the two beams collide, of course, the probability of something happening, of a collision happening, increases. So if you can increase the luminosity, you increase the amount of collision. And if you increase the amount of collisions, of course, you increase the data that is produced. So today we are here. And in the next 10 years, we are going to increase this luminosity by at least an order of magnitude, moving into something that will be called the high luminosity LHC, Large Hadron Collider. And look at this, so you see later, but look, there is something called the trigger rate, which is today 1 kilohertz, and it will become sort of an order of magnitude higher for the high luminosity LHC. This is important. So in terms of computing resources and storage resources, this means that in the next 10 years, the community, in order to keep working on this, will have to increase the capacity by at least something between 1 and 2 orders of magnitude. Now, if you take today's technology and you assume a standard evolution of today's technology for the same kind of price, probably in the next 10 years, you can get 1 order of magnitude more capacity. But this is not enough. So it is necessary to really look at different ways of working, different ways of processing information, and more performant, more efficient ways of processing information in order to cope with the requirements. You see this steep increase by the time of the high luminosity LHC for both computing and storage. So most of the research today, the technology research to support this, is about solving this problem. And so as a general overview, so there are 4 areas of painful activities. One is about just increasing capacity. Can we buy more? The second is increased performance. Yes, maybe we can buy more, but can we buy more performant, more efficient resources? The third item is about increasing efficiency. It doesn't matter if we have more, it's still not enough. We need to work better. And of course, we need to keep this at a reasonable cost. Our budget is flat. The contribution from the member states don't increase. So we have to keep the same cost during the years. So it's a very big challenge. There are 3 areas of investigation today. One is increased performance, hardware and software within the existing facilities. The second item is how to increase capacity by pulling together different types of resources, moving from our current distributed infrastructure, adding, for example, commercial clouds capacity or specialized clouds, or including supercomputer centers in the architecture, which is something that traditionally the high energy physics research has not done. And third is about really changing the way we work. And broadly speaking, today this is really a lot about artificial intelligence, or at least machine learning and deep learning flavors of artificial intelligence to speed up the different workloads and the different processes end to end, from data acquisition to the final probability distributions. Now, to make sure we use the same terminology, there are, this is very high level, there are a lot of missing details here, but formally speaking, there are four main computing activities, or four main types of workloads. The first one is data acquisition. This is really at the detector level. This is where the physics world of the collision becomes digital. Is the particles going through the detector are transformed into digital signals. So this is real time. And this is essentially done individually by each experiment. Each experiment has their own processing facility for filtering and processing, doing some initial processing of the raw data. The second step is to take all the dots, all the information, all the signals coming out of the millions of sensors in the detectors, and actually try to reconstruct what has produced, or what the shape, not yet exactly what has produced, but the shapes of the paths, the tracks along which the particles have crossed the detector. And this is a very difficult problem. It's highly combinatorial, and it is done with very sophisticated dynamic propagation techniques, Kalman filters, for example. But it's one of the future bottlenecks, and I show you why. Then, of course, is data analysis. It's going from this information and keep analyzing the data until the different probability distributions of the various events and particles are actually confirmed. And then there is a fourth part, which is about simulation. Simulation is, of course, needed to understand how to design the detectors, to understand how the detector works, and to know, to build a model of what you expect so that it can be compared with the analysis in order to confirm or a discovery or disprove a hypothesis. Now, let me start with computing. So I think you are all familiar with Moore's law. So there are a lot of discussions about Moore's law. Is it dead? Is it not dead? Certainly, in terms of a single-threaded performance, Moore's law is going down. It cannot be expected to keep the pace as it was until now. So the high-energy physics infrastructure today is mainly based on CPU. This is showing a number of limits. So we have started experimenting with many other platforms. FPGAs, not only for the data acquisition part, but for other types of workloads. GPUs, of course, neuromorphic computing, and quantum computing. This is still all very early, very experimental. There is nothing in production in terms of neuromorphic or quantum computing, but we need to start building knowledge today. So let me give you a few examples. So GPU acceleration is the first obvious choice. Probably our community is a bit late in terms of this. GPUs are already used in many other cases, but we are really talking about a very large scale GPU usage at this point. So this shows you, again, this is single-threaded, so the comparison is not really fair, but you can see this is essentially Moore's law trend and GPU growth. So GPU performance is increasing according to something very similar to Moore's law. And by the time we get to high luminosity LHC, the difference in performance, according to today's trend, will be orders of magnitude more. So we really need to transform our computing architecture to take care of this, to use this type of performance. However, this brings phenomenal software programming problems, because the software that's been designed until now was optimized for single-threaded performance of CPU, was designed in the past 20 years. And it has all to be redesigned or revised in order to actually use many core, multi-core platforms and exploit this performance. And from a cost point of view, this is now together becoming very interesting in terms of power consumption and performance price ratio. The other interesting area is FPGAs. FPGAs are already used and have been used for many years in the data acquisition for doing the initial triggering. It's a very fast selection based on simple rules. But in the future, they will have to be used to bring down to the real time as much processing as possible, to start doing some more complex and more sophisticated processing really close to the detector. So today the accelerator frequency is 40 megahertz, so there are collisions, 40 million collisions per second, and through the initial filtering and triggering, it is brought down to 1 kilohertz. And I showed you earlier, this is going to go up to an order of magnitude to 7, 8 kilohertz for high luminosity LHC. So FPGAs are used potentially in two forms. One as just FPGAs, but to do neural network, deep learning inference, very fast inference, very close in the initial triggering mechanism, and down the line, combinations of CPU and FPGAs to actually, again, do inference, but with more sophisticated deep learning neural network models as early as possible in the chain. This is very promising, and it is one of the main directions to be able to increase the trigger rate by 1 order of magnitude. And the next, but we are looking more into the future, is quantum computing. So today, of course, quantum computing cannot be used in production, but there are interesting possibilities in terms of simulators, but also in terms of physical devices. There are many companies already having put on the experimental market quantum computing device with 20 qubits of capacity, noisy capacity, so 20 qubits means probably 16 usable qubits, and there are devices moving beyond the 50 qubit total capacity in this year already. So this is becoming very interesting, and there are a lot of problems, combinatorial problems or classification problems that can be accelerated by using quantum computing. So we are doing a number of joint research projects with companies and other universities to do a lot of things, test simulators and devices, but also, for example, transform the algorithms so they can be moved from a classic form to a quantum form, and just because of that exploit this increase in computational performance. This is one example, it's for track reconstruction. So this is is a simulation, but this is how it looks like inside the detector. There are many collisions happening at the same time, and you have to look at all the points in order to construct this. So in order to start this process, you have to find what are called the seed points. And finding the seed points is a highly combinatorial problem that takes a lot of computing processing. So quantum computing is one of the hopes, one of the potential interesting technology to actually make this much faster and be able to cope with these increasing levels in the detectors. Storage is another painful point. Storage, in terms of storage, today I don't see any new breakthrough technology coming out. There is a fight between hard disk and SSD disk, solid state, and solid state are winning also for many reasons. They are becoming bigger and bigger, and bandwidth is much better. So we are probably going to move transition from mostly hard disk to mostly solid state. And there are interesting solutions, non-volatile memory solutions with a much smaller size factor, but they are a combination of RAM memory and non-volatile memory that introduce the possibility of a completely different in-memory type of processing. Storage is also, storage for us means storing the important things forever. We store around 80 petabytes of useful information every year now, and this cannot progress with current technology. So we are looking at, again, at future possibilities. And in this case, DNA-based storage shows some interesting properties. It has been announced recently that the first fully automated DNA prototype for storing and retrieving has been made available, again, experimental. And we are working with a couple of companies that are producing experimental devices with very interesting properties for the future. But we are talking about 10, 15 years in the future here. Cloud. As I said, we need to understand how to scale out. Today, CERN has the largest cloud computing infrastructure in the scientific world, not in the commercial world, of course, but in the scientific world. But we need to join this with many other types of resources. And one very interesting and very necessary point is to understand how to link cloud grid with high-performance computing. The high-energy physics is not high performance today, it's high throughput. There is a big difference. What we need is not necessarily to run everything very, very, very fast, but to have millions of jobs sent across the infrastructure so that the probability distributions can be built. And supercomputers are not good at that, and are not good at data intensive until today, data intensive execution. But machine learning and deep learning are actually changing all that. There is a convergence of the two worlds. So, and there is a lot of investment in all countries about supercomputers. So we need to understand in the community how to exploit better the efficiency and the performance that supercomputing provides, putting everything together. Artificial intelligence, machine learning and deep learning, as I mentioned, there are many interesting points about with a lot of potential in using this kind of technology. They can solve a number of bottlenecks, for example, for simulation or analysis, and decrease the amount of resources that are needed. And there are even, so this is something I find very interesting. So you might remember that Galileo used to say that the book of nature is written in the language of mathematics. And today there are ideas about the possibility of using natural language processing techniques to actually move from the raw data to the probability distributions, considering the two things as a language with the physics model as the grammar for this language. So there is no technology able to do this today, but in principle, if this becomes possible with this kind of technology, it really becomes the closest thing to using physics and mathematics as the language of nature and accelerating all these processes. Again, we are talking about probably the next 50 years, but it's good to think big and ahead. So one example for this is a simulation. Today, simulation is done using Monte Carlo techniques, very traditionally, very efficient, very detailed, but it doesn't scale well with resources. If you want to go to increase the precision of the simulation and cope with the increasing amount of collisions, you need to scale out resources massively. So we are looking into application, for example, of generative adversarial networks for this. So, I'm sure you know, but generative adversarial networks are a combination of two different networks. So you have a neural network generating something, a picture, for example, and another network looking at this picture, trying to detect whether it is a fake picture or a real picture. And if the network is not able to detect, it tells the other network. So if it is able to detect, it tells the other network, this is fake. Do something. And the other network generates a better image using this information. And if you look this, your image, your fake image, can become so realistic, so good, that it is not possible to distinguish it from the real one anymore. So if we take the simulation of a detector as a picture, as a very big picture, and apply this, we can generate efficient simulations in a much faster time, orders of magnitude faster, with much less resources. So this is one of the main directions of investigation for simulation. And quantum machine learning, again, new frontiers. There are many applications of machine learning technology, for example, support vector machines, that can be efficiently sped up on quantum computers. And by doing this, it might be possible to actually, again, speed up by orders of magnitude the analysis done. And this is an example of a classification of Higgs boson decays using this kind of technique done in collaboration with Wisconsin University, where it is possible to demonstrate, at least as a trend, that this kind of technology will really have a big impact in accelerating this kind of processing and increasing the overall computational capacity of the infrastructure. Now, I would like to move into a slightly different direction. So what I've told you until now is about the bottlenecks, the difficulties, the problems, and the technological opportunities specifically for high energy physics research. However, one of the objectives of CERN is to share this, is to do this in a collaborative way with other communities. Not only fundamental research is always a trigger for innovation and the creation of new technology. This has always happened. And these are a few examples of what has happened in CERN in the past few years. I mean, the World Wide Web was invented 30 years ago at CERN to manage the problem of sharing information. We use the technology used to create extreme vacuum inside the pipes where the particles run inside the accelerator. So you have to extract as much possible of air, otherwise the particles might hit molecules of air instead of hitting each other. So you really need to do extreme vacuum. But this technology can be used to create very efficient thermal panels that can keep 50 degrees of temperature below several meters of snow for many, many hours. Mechanical engineering, material science, radiation sensor used in medicine, for example. All this technology come out of the technology research to support fundamental research. So we started looking recently at better ways of working with other communities and communities that are producing more and more data today or in the future. And for us today, the most interesting community to work with is biology and medical research. Medical research and biology, if you put together all the different types of discipline, from genomic research to clinical trials and diagnostic systems, laboratory exams, and all that, is producing amazing quantities of information. So can we work with other communities and share problems and find common solutions? This is something that we really would like to do. So we have a few pilot projects in collaboration with other universities or laboratories to see how technologies we are developing for physics research can be used elsewhere. This is an example of a biological dynamics modeler, again, using the same techniques that are used for simulating radiation propagation. We are doing a biology parameters propagation, and it's a way of understanding whether, starting from basic principles, a few cells, behaviors, and particular chemical or electrical condition, you can actually simulate what happens in a real biology system. And we have managed to create very realistic simulations, for example, of the human retina mosaic growth, or to simulate in silico the growth of cancer cells in experimental conditions. So it is very promising, and again, the idea is to work in collaboration with other communities and to put this out in the open source software that anybody can contribute to and increase this kind of expertise as part of the community. The second example is machine-assisted diagnostic. This is also about machine learning and deep learning. We are trying to understand, especially, so this is the first case here, is trying to understand how to link input and output of a neural network. This is a huge problem. The neural networks are usually considered black boxes. You don't know exactly why you got a certain input, a certain output, or specifically which input produced a particular output. And this trust issue has enormous problems in many sectors. If you take, for example, autonomous vehicles. so buses or cars that drive themselves. If you cannot trust the decision of the system, you enter in phenomenal problems. If you're sitting there and the car has an accident, who is responsible? Is the car? Is the person inside the car? Is the manufacturer of the car? Is the software engineer? So the possibility of making this process more deterministic is important. And in this case, it's a medical application. You have genetic mutations in the DNA of a person, and this transforms into physical aspects. How can you use, for example, image detection techniques to recognize a small part of the face or the fingers of the body and link this to a specific genetic mutation in the DNA? If this can be done, it would allow very early detection of very important neurological or tumoral diseases. But it is necessary to understand which particular gene mutation or gene expression has produced a particular physical condition. And the second aspect is automatic diagnostic systems for people. These are virtual doctors, some entity that you can talk to, express your symptoms, and this entity will do an initial filter of condition and then send the person to the most appropriate specialist and speed up all the procedures, especially in countries, in situations where the specialists are not always immediately available. In general, medical data analysis, it's a huge problem. As I said, the amount of data being produced is phenomenal. It's really hundreds of exabytes already today. And there is a huge problem simply of collecting data. Everybody's collecting data. There are dark databases of hundreds of terabytes sitting anywhere in the world. But actually, it's very difficult to act on that data, to do something with that. So we are building, again, is a test platform to test the technologies that might help that and help standardization. And for example, one interesting project that we are starting now on this kind of platform is about efficient data encryption, something called homomorphic encryption. It's a technique that allows you to do deep learning, to create deep learning models, encrypted models, that don't have to be decrypted in order to be analyzed. So you can transfer information, sensitive information containing personal information or medical information across the network and put together as much data as possible from different hospitals and different conditions and try to understand very rare and specific conditions. So this is a project that we have in common with, we are running with a number of hospitals and companies working in this sector. And finally, this is something that I'm very proud to talk about here, because this is a project we have just started in collaboration with the Samara University, which is about trying to use, again, machine learning, deep learning techniques to do early preventive maintenance, predictive maintenance of complex engineering systems. We are using as a use case linear accelerators, both for research and for medical applications. And the idea here is to understand whether it is possible to detect as early as possible anomalies in the way the linear accelerator are working, and warn the operators of the machine in time in order for parameters to be changed or parts to be replaced, and in doing that, reduce as much as possible not only the number of problems but also the downtime. So if you have a hospital with this kind of machine, if the machine has to shut down for 6 months for repair, it's a huge loss in terms of human life. So if we can understand how to detect this as early as possible and do really personalized predictive maintenance plans for individual installation, this would, first of all, would save lives, but also would save a lot of money for laboratories and hospitals in many conditions. So it's a very interesting project, and I'm really interested in seeing where this is going next. And this is a small example. We are also working with the United Nations organization, UNOSAT, to speed up the satellite image analysis, again using deep learning, machine learning. These are all social activities, social research with social impact to find ways of increasing the usefulness and the value of what we are doing. Now, just briefly to conclude, how are we doing it? So I mentioned I'm in charge of CERN Open Lab. CERN Open Lab is in the IT department of CERN. It is in charge of running and identifying these research collaborations with industry and research and academia. So there are four main activities. Of course, the research activity itself, and the work in collaboration with other communities, medical research, life science, and so on. And the other two important activities are communication and education. Communication is very important. We need to explain what we do. And I spend most of my time really talking to people and to companies, the universities and researchers to try to understand the value of collaboration and identify the right opportunities for working together. And finally, education. This is a huge, is both a problem and an opportunity. And it's good to talk about this in a university. So what we see is an important gap in terms of skills projected across the next 5 to 10 years. If you are going to introduce all these new technologies, how do we make sure that the engineering and the technological skills can keep the pace? So we are organizing with communities, with universities and with companies, educational programs and research programs also targeted to students. You can see here, this is a snapshot of all the collaborations we have at the moment. And yes, you're here. Predictive, proactive maintenance. So in collaboration with all this, we do research, but we also do education and training. And I would like to take the opportunity to showcase what we call the Open Lab Summer Student Program. This is dedicated to any type of scientific students, computer science, mathematics, physics, it doesn't matter, as long as their talent and skills are a good match for the problems we are trying to solve. So every year we can host during the summer around 40 students, and we receive between 1,500 and almost 2,000 candidates every year. So it's very competitive. But the opportunity is to stay 9 weeks at CERN, working with us, working with the companies, working with other institutions, and really solve practical problems in any one of those areas that I mentioned until now. So in conclusion, I will not go through all that, but I have a simple message. We are really living in a very interesting moment of scientific and technology history. This fourth paradigm, it's becoming very complicated. It's something that I believe no individual person can address on their own. It's really a matter of collaboration. But we are really seeing a sort of tipping point of technology. Until now, in the past 5-10 years, I've seen improvements of existing technologies, but now really new technologies, real breakthrough things are coming up that we can exploit, and we have to learn how to exploit this. But opportunities, but also responsibilities, again, in terms of education, in terms of collaboration, in terms of working with other communities. So there is a lot of work to do, and again, I'm very happy to be here and talk to you about this. If you have ideas or recommendations, suggestions for collaboration, interesting things you want to do together, I'm always listening, so please talk to me anytime. Thank you very much.
Thank you very much indeed, and now we have time for questions. Yes, please, but please use microphone.
I have a rather general question.
Sure.
You mentioned the 4 steps of science development.
Yes.
Could you show first slide? So the first step is empirical data. Second step is theoretical. Yeah, and third step is computational, and fourth data-driven. What do you think about striking similarity of first and last steps?
Absolutely. Yes.
Maybe we have here historical spiral, and
Yes.
history just repeats
Repeats
itself on high
Uh,
level.
Yes, thanks. It's a very interesting comment. I agree. Actually, I mentioned that today, until now, we have used the standard model. It was a nice description, and we could look for something. And today we are sort of reversing this. Since the models are not precise enough to allow looking for something, we are really reversing the process. We are collecting as much data as possible and trying to see what emerges from that data. So empirical, reproducible, and structured observations are really becoming, again, the base for most of the research. I totally agree.
Thank you very much. Other questions?
Nope.
No more questions? Oh. Okay. Could you use microphones so that other people could hear you?
I agree, it is the loop. The issue is only that empirical observations allowed us to interpret that by human beings. And here we basically data-driven science, we are focused on emergent systems. And my question is, that's what I was trying to tell last year. We just want to discover from data new theories, basically, in designing, basically, and creation new materials and so on. So do you have any framework for emergent systems?
No.
No, not yet. Okay.
No, not yet.
And the second, I assume that quantum computers you have from IBM.
As well. So we are working
But
with...
do you get for free or you have to pay?
It depends... it depends on the system that we want to use. There are a number of systems that are openly accessible and other systems that are not openly accessible.
I see.
I cannot talk about the access mechanisms that we have in place.
Okay, thank you.
Thank you. Other questions? In this case, I suggest that we thank our speaker. And this is the end of the session. Thank you very much for attending it.